Okay. So hi, everyone. Thank you for coming to my presentation today. My name is Kaitlyn Etienne, and I'll be presenting my final master's project for the University of Arizona MSGIST program on assessing national parks for emerging climate trends using space-time pattern mining. I wanted to thank my graduate advisor, Dr. Jennifer Mason, for the support, and then I'll lay out my objective. So setting out, I wanted to conduct a physical climate risk assessment using GIS tools. And I eventually decided to focus on national parks as my study area. I wanted to look at historical temperature and precipitation data and understand what potential climate patterns US national parks may be exposed to. I chose US national parks in part because I know that they were selected due to having some kind of typically ecological or historical significance, and climate can have an impact on ecology. So in my research for this project, I was reading one paper actually that came out of the University of Arizona, and it was going into detail on local extinctions, or the concept of local extinctions, where species ranges are moving due to climate changes, and they're not necessarily becoming extinct overall per se, but they're becoming extinct in the area where they used to live. And the finding of this study was that across multiple geographies all over the world, local extinctions are already very widespread. I believe they concluded about 100 species of those that they had looked at were already experiencing local extinctions and shifts in range due to climate change. For my study area, I chose the contiguous United States. As you can see, here's the national parks data set that I used. My data sources also included temperature and precipitation data by county from NOAA, as well as the US Census counties layer. And I knew that my analysis would have to look at trends across both space and time. And so I elected to do create space-time cubes with my data, and then run an analysis on those. So I started by exporting June and December temperature and precipitation data at 10-year intervals from 1900 to 2020 from NOAA. From there, I reformatted it a bit, and I was able to build 4 space-time cubes using ArcGIS Pro. So you can see on the right, this is an example of a space-time cube. It's a 3-dimensional cube where the z-axis is time, and you basically created a bunch of time steps that stack on top of each other. I ended up making 13 time steps out of my data. And then from there, I ran an emerging hotspot analysis on precipitation and temperature values and anomalies. And I used the Geddes or GI star statistic and Mann-Kendall trend test to look for statistically significant patterns in spatial clustering over time with a significance of 90% confidence level or greater. Overall, trends in mean temperature and precipitation across the entire contiguous United States were not found to be largely statistically significant. I did note one statistically significant trend, which was an increase in June mean temperature. But I really wanted to understand the local patterns that were occurring across the United States. So I made a series of maps to represent the resulting space-time patterns. These designations were developed by Esri. They're all here. You could see laid out in the legend on the right side. I won't go into detail on each of the patterns, but I'll give an example of one. So you can see here in the northern part of the map, the December temperature values are showing intensifying cold spots. This means that the location has been a statistically significant cold spot for 90% of the time step intervals, including the final. And the intensity of clustering in each time step is increasing overall, and the increase is statistically significant. So each of these designations is essentially showing patterns that are a combination of the space and time variables. here's my June temperature map. So this is where you could see hotspots and consecutive hotspots, new hotspots, and intensifying hotspots, all showing up throughout the South and the Southwest. And again, this was the one, the June temperature values was the one variable where I did see a statistically significant increase across the entire contiguous United States on average. But here it is kind of laid out and spatially where this is occurring. I wanted to visualize patterns that were just happening within the boundaries of the national parks. And so here you can see I was able to do that for the temperature values and temperature anomalies. In the top left chart for June temperature, I did note that 12.7% of national park area falls within the intensifying hotspots, which I saw on the previous map. And so this is kind of how I chose to break down this data and observe changes within my study area. But I noticed some more interesting trends in the precipitation data, so I'm going to jump into that and then do a deeper dive there and explain what I found. So here for precipitation, in the top left charts for June precipitation values, I saw historical cold spots in 6.4% of national park area. So that's an area that used to be a cold spot, but it wasn't significant in the final time step. In the top right for June precipitation anomalies, I saw new hotspots happening in 6.5% of the national park area. And that's a hotspot with new statistically significant clustering in the final time step. And then in the bottom right for December precipitation anomalies, I also saw consecutive hotspots for 12.3% of national park area and new hotspots for 3.2% of national park area. And the reason I was interested in these changes is because they're all of these patterns, new hotspots, consecutive hotspots, and historical cold spots are indicating changes that happen in the last 1 or 2 time steps of the data set. So from these findings, I did conclude that some statistically significant emerging precipitation patterns appear to be happening in areas where national parks are situated. And on the next couple of slides, I'll go into a bit more detail on where these patterns are happening and which national parks are mapping to each of these patterns. So here for the June precipitation values, you could see the historical and actually a number of diminishing cold spots as well, showing up largely in the western parts. If you could see my mouse here, parks that mapped to these patterns included Yellowstone and Grand Teton National Park, specifically within the historical cold spots for precipitation values. For June precipitation anomalies, there were new hotspots occurring largely situated in the Northwest, as you can see here. This is the red pattern in the center with a white border. And the parks that were affected here included Glacier National Park, up here in the north, Crater Lake and Redwood National Park over here in the west. And then again, parts of Yellowstone were overlapping with that new hotspot pattern as well. And then finally, looking at December precipitation anomalies, I saw a large area of consecutive hotspots showing up in parts of the Southwest, which is right here. So these included Zion National Park, Glen Canyon, Dinosaur National Monument, and parts of Death Valley. And then over in the Mid-Atlantic region, you can see new hotspots showing up. And some of these are cropping up around the Appalachian Trail. And you can see further towards the north end of the Appalachian Trail, some consecutive hotspots as well for precipitation patterns. So in conclusion, the study was a spatial analysis of historical climate data, including temperature and precipitation. And I used space-time pattern mining to see where local changes in climate might be occurring throughout the contiguous United States, and especially in areas where national parks are situated. I did see that in some areas where national parks are, there appear to be some statistically significant emerging precipitation patterns, historical cold spots, new hotspots, and consecutive hotspots, which points to kind of a general increase in precipitation in those areas that's newly emerging. However, I think that more research would be needed to understand what these might mean for the long term. And I also think that using a larger climate data set in a future study could help to clarify whether these are truly trends or if they perhaps represent outliers or just a short-term upset in the typical climate pattern for that area, since they are based on just one or two time steps. In the future, I'd like to incorporate climate projections as well to have a forward-facing component. It's actually something that I wanted to do really, really badly for this project. But the format of the data was a lot of large raster data sets and just a little bit different to work with than what I ended up finding and using for my historical climate data analysis. But I think some kind of combination of historical climate data and then looking at the forward-facing projection component would be interesting if I were to do a longer study. Yes. And with that, that's kind of the end of my talking session. I can leave time for Q&A. I can go back to any of the slides as well if there are any questions about particular things happening on the maps, but that's kind of the conclusions of my study.